Okay guys, we are here in the chemistry lab and we are getting set up to do the LeChâtelier's principle lab. Okay. Now, the way we run this lab, we run it through a demonstration to show you some different changes as we kind of do this. And then we give you guys some follow-up questions that you do as you work your way through this. Okay. So if you take a look at our lab, what we have going on here, we have your introduction. So please read through this about the reversible reactions and kind of how the LeChâtelier's principle works and that kind of stuff. And we're going to do the demonstration part here, which is the cobalt system. Okay, so our cobalt system has a combination of a blue complex, which is cobalt chloride -2 charge that you see on your screen there, and a pink complex, which is cobalt and water mixed together in an actual complex put together by intermolecular forces that is pink. Okay, and it's at equilibrium with itself. So as the reaction runs, you can actually force this reaction to be more pink or more blue depending on which way you push this reaction. Now, if we recall, the LeChâtelier's principle tells us that if we stress our system, we're able to then shift the equilibrium to respond to that stress. So we're going to go through a series of stresses here in terms of this equilibrium in this system. Now, these stresses are listed down here for you guys in your document. So what I want you to do now is take a look at all these different things that we have. We're going to heat this thing up using a Bunsen burner. We're going to put this into an ice bath. We're going to add 12 molar hydrochloric acid to this. We're going to add water to it. We're going to add potassium nitrate to it. We're going to add silver nitrate to it. And we're going to use an air pump to add pressure to this. Okay? So what I'd like you to do before you move on with the video is right here where it says resulting stress, you determine what that stress is. So is it warming things up, cooling things down, changing a concentration? Is it adding pressure, removing pressure? What is the generic stress that these things are going to cause? Okay? And then I want you to predict what direction this equilibrium will shift. So let's say, for example, with the Bunsen burner, if we say that that stress is warming it up, okay? If it warms it up, which way will this equilibrium shift? Because heat is exothermic over here. So if we heat this thing up, will it shift back left or will it shift towards the heat to the right? Make that determination before we proceed. As a result, predict the color change. So you're going to do a lot of work before I actually even run the demonstration for you. So predict your color change. So if you think it's going to shift to the right, you would say it becomes more pink. If you think it's going to shift to the left, you would say it becomes more blue in terms of your equilibriums, okay? Once we have this filled out, then we'll actually observe the color changes and see them happen, okay? So if you would please pause the video now, okay? And this is kind of important because if you don't pause the video and you just see it happen, you don't ever engage your brain into the thinking process here, and what you're going to have to do come quiz time, all right? So please pause the video here, go through each scenario, identify the stress, the direction of shift. You can just use arrows here if you want to, left and right arrows, or none possibly. And then predict your color change, more pink, more blue, or none possibly here. And then once we get done, we'll do it together and see what actually happens. Okay? So I'll give you a minute to do that. So pause the video now, and then we'll move on. All right, so thank you for doing that. Here we go through our different scenarios. So the first thing we want to do is we want to move over to the iPad, take a look at what we have going on here. So again, here's an example of the equilibrium that has shifted very far to the blue side. Okay, so I've preset this up where this is shifted predominantly on the reactant side right here. So we see that kind of visual here. Over here, we see it shifted really far to the product side. Okay, where we see that kind of pinkish color coming from there. In the middle, we have our little flask here, and that flask is sitting somewhere between these two values, somewhere more in the middle of that, okay? So what we're going to do is we're going to take this sample of it. This is the one that we're actually going to change. We're going to leave this guy sit here the entire time. That way we always have a visual of where we started versus the extreme to our left and our extreme to our right here, okay? So the first thing I want to do with this guy is I'm going to heat this thing up, okay? So I come over here, and now I'm going to heat this thing up. So I have a hot plate. It says Bunsen burner, but really any heat source will work for this. The gas happens to be turned off in the room today, so I couldn't use a Bunsen burner. So here we go. So we see our example here. kind of a purplish color we see now. And we're going to slide that into our hot plate. Just going to swirl it around. It doesn't take very long to do this. We just got to warm this thing up and let it happen a little bit more. Hopefully you can see it inside of the actual thing, but if not, we'll come over here and we notice we were here, and now as we warm this up, we shifted the equilibrium to the left and we made it more blue, okay? Which would make sense because if you look at this, we're going to add heat to it. So adding heat, and the product side is where the heat is, so the way it's going to respond to that shift, or the way it's going to respond, is we're going to go away from the heat, okay? So we warmed it up, so the equilibrium is going to shift to the left to try to absorb that heat energy that we're putting in, all right? So that's what we see here, is we see that shift to the left because we added heat, and heat was on the right-hand side. So the response to this is it's going to shift left to counteract that, all right? Now, we heated this thing up. What do you think is going to happen when we do the opposite? Okay, so doing the opposite, instead of heating it up, we're going to do an ice bath. So we now have our same solution. This thing is pretty blue. I'm going to add it in here instead. At first glance, you might say, whoa, that thing looks like it's even being more blue because of the ice and that stuff in there. But we'll let this thing cool down. And it doesn't take us very long, swirl it around so we kind of get a good even mixing of this. And we see that as this thing cools down, hopefully you're getting that visual, that we have now shifted it back to kind of our equilibrium. If I continue to cool this, I will continue to get more and more of that kind of pink looking flavor to it. And if we see now, we actually are more to the left. We're not as far over as this, but we're definitely lighter than that value that is right here. So we're somewhere in between here, which again would make sense, okay? So let's work our way through the thoughts about this. As we cool it down, we're taking heat energy away, so we're removing this. So the response to the equilibrium is to replace it, okay? So we remove this, so the equilibrium is going to shift to our right, which is going to replace that heat energy, or to release that heat energy to replace it, which causes a more pink color in our equilibrium here, okay? So that would be the cooling process for doing this one. All right, and the thoughts behind it. Now, the next step here is we have cooled it. We're going to add 12 molar hydrochloric acid to this thing, okay? Now, looking at our equilibrium, we may notice that there is no HCl in this reaction. No HCl here, no HCl, no HCl, no HCl, no HCl, okay? So our equilibrium might say, well, this will have no effect, right? There's no hydrochloric acid in this, so it has no effect. However, you have to remember that hydrochloric acid, when in solution, remember, it's a strong acid, which means it's a strong electrolyte. So really, the hydrochloric acid, once we put it in solution, is going to split. There's going to be lots of hydrogen ions there, H pluses, and there's going to be lots of Cl minus there, okay? So a lot of the hydrochloric acid really isn't about the hydrogen. It's about the fact that we're going to be putting a lot of Cl minus into this reaction, okay? So adding the HCl is actually adding chloride ions to our solution, okay? This would have worked if I just added table salt too, okay? But I chose hydrochloric acid. So we're going to add a lot of chlorine ions in here. So if we're adding chlorine ions in here, we're going to stress the system by increasing this. So it should shift to our left to absorb those and become more blue. So let's see if that's what we see happening here. So here is our solution. And I'm going to take just a dropper full of our hydrochloric acid and squeeze it in there. And sure enough, it does not take long for this to happen. Come over here to do our comparison. And we see that by adding the hydrochloric acid, we increase the chlorine ions in solution. As a response to that, the equilibrium is now going to shift to the left to absorb those extra chlorine ions. It's going to make more cobalt chloride complex. It's actually going to make a little water here. We don't see that because it's colorless, but we see that blue color happen because of that shift in there, okay? Now, the next thing we're going to do this thing is we're just going to add water, okay? Just plain Jane water. And you might think, oh, adding water, that won't affect this thing at all. It's just, I mean, water's water. There's already water in here. No effect, right? Take a second look, though. If we go back to our equation again, water is part of this equilibrium. Okay. Now, we wouldn't write it in the equilibrium expression, but water is a component in this, and it can affect the overall result here. So if I add water, I'm going to make more water, which then should stress the left-hand side of the system. So it should move to the right to absorb that stress, creating more pink. And let's see if that happens. So we're going to add a little bit of water in. And sure enough, it does not take long. Add a little bit of water, and we see very much a shift from our middle down to the pink side of our process here. Okay? So again, we see that shifting as this equilibrium reduces that stress as we go in here. Okay? So that is our next step in this process. All right? As we continue on, we have some more things to do. The next thing we're going to do is we're going to add potassium nitrate to our solution. Okay? So we have our solution here. It's a little bit pink. I'm going to bring it back a little bit closer to our original. So I'm going to add very carefully, add a little bit of hydrochloric acid. Not much, but I'm going to add just enough so we get kind of back to that purplish color we had before. That looks pretty good. We don't want to get too far to the blue side either. And sure enough, here we go. We have a nice kind of purple color now, more close to that equal part that we started at before, right? And now I'm going to add potassium nitrate to this system, okay? I'm going to add solid potassium nitrate because I really don't want to add any more water to this thing. I just want to add the crystals in here. Now, potassium nitrate we know is really good at dissolving. So I got potassium nitrate here. I'm going to pour it in here. I'm going to swirl this thing around. And as we see this swirling, we see absolutely nothing happening, okay? So we were right about here. We stayed right about here. We were kind of a little bit lighter than our original when we started. Nothing happens here, okay? So let's talk about why nothing happens in this scenario, all right? So when we add potassium nitrate, remember, potassium nitrate, as it dissolves into this solution, I can keep swirling it and try to get more of that to dissolve. We're adding potassium ions. We're adding nitrate ions, okay? So potassium ions, nitrate ions in the solution. If we go back to our equilibrium expression, there is nothing here that relates to potassium or nitrate ions. There's nothing here that causes a precipitate. There's nothing here that the nitrate's going to affect. There's nothing here that the potassium is going to affect. It's just going to be another spectator floating around in solution, okay? So because the potassium ions and nitrate ions have no effect on any of these things, we get no result with this thing. So this basically does nothing, okay? So there are cases where you can add things to an equilibrium and it has no effect on it. And this is one of those examples here, okay? Now, the next step is we're going to add silver nitrate. And I don't have silver nitrate in its powder form. I have it in a very concentrated solution. So we're going to be putting a little bit of water in this, but really it's going to be a lot of silver nitrate that we're going to be adding to this thing to make this happen, okay? Now, let's take a look again at our equilibrium. So there's no silver anywhere in here. Again, there's no nitrate in here before, okay? We already know that nitrate has no bearing on this because potassium nitrate had no bearing, so the nitrate part is not going to be anything that's going to go on here. So the question becomes, what will silver do, if anything at all, okay? Is this just another example of the exact same thing? Probably not. All right, so here we go. We have silver nitrate to put in this thing. Now, silver, if you recall, if you look at the solubility chart and silver and what it is, silver is not a very soluble substance. It is soluble in nitrates. However, silver is not soluble in chlorides, okay? So if you put silver ions with chlorine ions into solution together, the silver will bind with the chlorine to make silver chloride solid, okay? So let's see, will that affect our equilibrium? Well, I have chlorine ions in solution. So if I'm adding silver to this, the silver ions will bind with this chlorine and it will remove the chlorine in solution, okay? It'll now be part of the compound silver chloride. Thus, it's leaving the equilibrium. So essentially, by adding the silver, what I'm doing is I'm actually removing the chlorine ions from this equilibrium. So if this removes away, what we should see happen is we should see that it wants to run to the right to replace what's being removed, and we should see pink happening here, okay? So let's test this idea out. So we're going to add some silver to this thing, and you notice it gets very white very fast inside of here. And that white powder that you are seeing is actually the silver chloride that is being produced. And we'll add a little bit more into this thing, and we're going to swirl it around so we see the result. And sure enough, if we go back to our example over here, we were someplace about here, and now we're much closer. In fact, we may have even gone beyond that in terms of how pink this thing is now in comparison with this, because we made it that much more pink by adding that silver there, okay? Silver took the chlorine away. The reaction shifted to the right to replace the chlorine, thus creating more of the pink solution, which is the one on the right-hand side of this. All right, now, those are all different stresses that we've happened. Now, the last one is a little different because I can't do the air pump and that kind of stuff. I can't do that in the test tube. But instead, I have this guy for you. All right, so what I have here is I have the same solution at the same equilibrium we had before. This is our cobalt complex inside of here. That's, again, that kind of purplish color that we see going on here. And what I have it set up now is I have it hooked up to a normal bicycle pump that is sitting at 0 psi or no pressure, okay? So what I'm going to do is I'm going to add a little bit of pressure to this, and we'll see what happens, okay? So just put a little pressure in, feel the container's pretty hard now. I don't want to put too much in. I don't really trust this plastic a whole lot, okay? I've gone from 0 psi to about 15 psi in there. I don't know if you can see the gauge or not from the way I'm rolling this angle around here. So I put about 15 psi of pressure in here, and we're seeing nothing happen again, okay? I'm not going to go any farther because I know nothing's going to happen, and I really don't want to risk possibly cracking this open or doing something. But just to prove we have pressure in there, which will open that up, and sure enough, hopefully you could hear that releasing the pressure. And again, we see nothing happening with this. This stayed that kind of purplish color the entire time, which should make sense because if you go back to our equilibrium again, there is nothing in this equilibrium that is a gas, okay? So we do not have an unequal molar value of gases in our equilibrium. It's 0 on the left, 0 on the right, so they're exactly the same, which means pressure should have no effect on our equilibrium, okay? All right, guys, that was a lot. We went through all of them. Hopefully, you guys, if something was a little confusing, you can stop the video, rewind it, and go back and kind of think the thought process through. But those are the kind of things we have to think about as we look at how does LeChâtelier's principle help us understand how when we stress a system, it's going to shift to partially offset that stress and to relieve that stress, okay? Now, for you guys, we've done this one together, and you've seen it happen. Your job now is to go down and explain what is going on here through what we just talked about, okay? So I did a lot of this work for you in terms of how's it shifting, what's going on here. So fill in this table now based off of our conversation through all that kind of stuff. Once you're done filling this out, then you're on your own for a few systems, okay? Our next system is a chromate system. You have yellow chromium oxide or chromate ions, and you have a very dark red dichromate ions in equilibrium, okay? Here's an image of what that looks like in somewhere in the middle point of that equilibrium, okay? And then we're going to tell you what's going to happen if you add this, what's going to happen here, and then if you click on this link, it's actually going to show you a visual, like a picture, a before and after picture of what happens in this, okay? Then we're going to go to an ammonia system. Again, we have our ammonia, okay? We're using this purple color. It comes from this indicator called phenolphthalein. Now, phenolphthalein turns purple in the presence of hydroxide ions, or kind of a pinkish purple color. So this is going to be our only visual cue here. So again, you're going to stress the system, predict what's going to happen, and explain it. Click on the link. That will tell you the before and after picture of what goes on. And then finally, we have a nitrogen gas system, which also is the same setup. So here's your equilibrium. You have a colorless gas. You have a brown gas. You see it kind of looks almost a yellow in between the two here. Answer the questions, click on the link, and then once we've submitted this and we've had it all done, you'll be able to click on the answer key and solution, so you'll be able to see what the right answers were and have that prepared for you before you take the quiz on LeChâtelier's principle. All right, guys, that is it for this video lesson. Hopefully that can do it for you so you can get through the lab and take care of your part of it. Again, we are working with our lab partners on this, but each person should be submitting their own responses to this. But please do collaborate with each other as best you can and work with each other to finish up this lab. Thank you.